In this video, we're going to deal with conservation of momentum in multiple dimensions. And at times, this can be one of the more challenging topics of our mechanics unit. So don't be afraid to go and watch this video a couple different times if you have a problem similar to this, so you can be able to understand what we're doing as we're going through this problem. We start off with just a simple ball striking another ball. We have red and blue just to kind of make it easy to understand which ball is which. Our blue ball has a speed of 1 meter per second moving to the right at a red ball that has no velocity at all. After the collision, you can see that our ball gets deflected upward at a speed of 0.4 meters per second at an angle of 35 degrees. The question is, what happens to the red ball? Where is this one going? Intuitively, we can kind of say, you know what, if this is moving up, this better be moving down, because if momentum's conserved, we only have momentum in the x direction over here. And that might be a good place to start. That, you know, if we say, okay, the momentum P in the y direction initially is equal to 0. So the momentum at the end, momentum in the y direction final, has to be equal to that. Our x direction is a little bit different. A momentum in the x direction is only going to be influenced, I'll put a little I here so it's the initial, is only going to be influenced by the blue ball. And that's just simply going to be mass times velocity, which in this case, the numbers are pretty simple, 0.15 kilograms times 1 meter per second. So the total momentum in the x direction to start with is just going to be 0.15 kilograms times meters divided by seconds. So that means this is the only momentum we can end up with. We can't have any momentum moving in the y directions when you total the two balls together. So that's kind of our start of thinking about how this momentum is going to be conserved and what is going to have to be our final momentum. But this is going to come into play later on. Before we can kind of figure out what this red ball is doing, we have to first find the momentum of the blue ball. So if you notice, this is going to kind of form a nice right triangle. We know there's going to be so much momentum going in the x plane and so much momentum going in the y plane. I guess to start, I just want to find the new momentum. So I'm going to find the final momentum of the blue F when it's going off at that thing, which is just going to be simply an MV problem again. So P equals MV. I'm going to start putting my numbers in, 0.15 kilograms times my velocity, which is 0.4 meters per second. And my calculator had this already worked out. It's 0.06 kilogram times meters per second. So this is what our momentum is going up in this direction. Now that momentum triangle is the same as this velocity triangle. So we end up getting something going this way, 0.06. And we have two different parts of this. So much of this is going to be going in the x direction, and so much of this goes in the y direction. And to find this is just our good old sine and cosine function. This is going to be the same 35-degree angle. So if I want to find the y, that is our opposite side, or our sine. So sine 35 degrees is equal to py divided by 0.06. Now that's kilogram meters per second. I'm going to leave those units off because it gets it a little easier to not have to write quite as much. Our momentum in the y direction is going to simply equal 0.034. Keeping our two sig figs, kilograms times meters per second. Our x direction is a similar idea, but this time cosine function. I'll put that down here. Cosine 35 degrees is equal to px over 0.06, and our x momentum, px, is going to equal 0.049 with two significant figures. So, okay, what does that tell us? Well, these two numbers are very important. That's our py, and that's our px. So, I guess kind of starting, we know that if this had 0 y momentum, it's going back to this idea right here. It has to have 0 y momentum at the end. So this has some momentum going up that's equal to 0.049 3, 4. So if we know anything right now, we know that this red ball has to have some momentum going down. That's equal to negative 0.034. And the negative is not super important. It's one of those things that we have to know that negative just means it's moving downward. It really doesn't affect our trig functions and stuff like that. So that's kind of our first thing is, and let's switch over to a red pen here. Our final momentum in the y direction is going to equal negative 0.034 kilograms times meters per second. So the next question is, well, what about the x dimension? What happens in the x dimension? Well, we got to kind of go back to this idea that our total x is going to be 0.15, which means that it has to be equal to our final x. So if I say, okay, this is for the total, it's 0.15, that comes from a momentum from the blue ball final plus the momentum from the red ball final. And I'm going to kind of just move this over. 0.15 is equal to the momentum from the blue ball, which is 0.049, plus the momentum from the red. So our final red momentum is going to equal 0.101 kilograms times meters per second. So what this tells us is we know the components of this. We know it has a y component of this. We know it's going to have an x component. Let's put a little x in there to add another subscript of that. Now we need to slide down on this page just a little bit. And I'm going to kind of, we need to redraw our triangle. So just to kind of finish this up, I'm actually going to switch colors, which might be a little bit confusing. We'll go to a green color here. We basically need to figure out what is our final momentum for the red ball. And we just kind of figured out using the numbers we have up here, and I'll redraw them because it's a little bit tough to see the way we have to shift the screen. We have 0.101 kilograms times meters per second going that way, and going down this way we had 0.034 kilograms times meters per second. And that's going to make a new triangle that's going to give us the final momentum for the red. And to find this is a right triangle. We're going to need this angle eventually, but we don't need it right away. We can just simply use the Pythagorean theorem. So the momentum of the red squared is equal to 0.101 squared plus 0.034 squared. And this is something I'm sure you've done enough Pythagorean theorem that it's really not even that big of a deal at this point. So I'm just going to write down the momentum of the red is equal to 0.11 kilograms times meters per second. Now we can find this angle using the tangent function, and that's opposite over adjacent. So the tangent of theta is equal to 0.034 divided by 0.101. Theta ends up equaling about 19 degrees, again using our two significant figures. Now you could use sine, cosine, it didn't really matter. I used tangent because I use these two original numbers. It's up to you what function you want to use for that. So we're in our home stretch. Now if you kind of remember, if I go back up here, the question was, what is our final speed? We found the final momentum, but we want the speed. Sorry about that. We want the speed of this. So if you remember, momentum is equal to simply just mass divided by velocity. So velocity would be equal to momentum divided by the mass. So in this case, my momentum is 0.11 kilograms times meters divided by seconds, divided by the mass of this, which is 0.20 kilograms. You can see that's going to cancel, kilograms cancels off. My velocity is going to end up equaling 0.55 meters per second. Now, that's not really a true accurate account of what's happening. We know this is moving down. We need to include a direction now. There's two ways we can handle this angle. We could call it negative 19 degrees, which is fine. We could take 360 minus 19 degrees, which is equal to 341 degrees. I personally like the negative 19, so I'm going to put at negative 19 degrees. So that is our momentum in multiple dimensions and how we can use that to find our velocity. You could use this kind of process to find momentum and all kinds of other things with this. But if you have issues with this, don't be afraid to go back, rewind. That's the beauty of the video. You can do it at your own pace. So that concludes this example.